Welcome to chapter 15, the search for more acid. Yes, Tyler. There's only one more chapter after this, electrochemistry. Yeah, we are approaching the end of AP Chemistry, which means you now have learned two semesters worth of college chem almost, right? Lots of college chem. Okay, so in chapter 15, we're going to start with kind of this weak acid idea again, but we don't just have the acid, we will also have the conjugate at the same time. We might have the acid and the conjugate at the same time, and they kind of have like a little balance. And for those of you who are just watching the video, I'm holding stuff in my hand and going back and forth. It's Casey's phone and a trash can. Now, I wouldn't do that. So here we have acetic acid. It produces hydrogen and acetate. But we might also have acetate come from a salt, like sodium acetate. So we could have acetic acid and sodium acetate put into the same flask. One of these breaks apart better than the other. Group 1 elements are ridiculously soluble. Sodium, being a group 1, is going to ditch all of its acetate, and so however much sodium acetate you put in the water, it's going to free up all of this acetate. Do you remember we did the two types of acids before? We had like a Ka that was big and a Ka that was small. Which Ka did we deal with first? The big one. Well, the equilibrium constant for group 1 salts is huge, and it shifts all the way over. So all this acetate is freed from the sodium acetate, but this weak acid is not as big, so we would deal with that secondly. And that means there will already be acetate in the water. That is going to slow down the ability of this acid to work. And I think the best way to do this is to just actually look at math. So you have this completely worked out in your notes, true? Let's just kind of look at what's going on. So Matt has to calculate the pH, percent dissociation of this acid. He's got 0.2 molar acetic acid, and here it's Ka value. It's just acetic acid in water. So here's what we were doing last chapter, just like 5 minutes ago. 0.2 minus x. Why am I assuming this is just equal to 0.2? X is negligible. Very good. Good job, Arthur. And therefore, what we produce over here is equal to what we've lost there. The Ka is equal to the products divided by the reactants. Cross multiply, take a square root, got the value for x. Calculate the pH. The pH is equal to the negative log of x. And I got the pH, so it's 2.72. That answer might be off by as much as 5%. So it might be 2.73. Big deal. You know, when I mean off, I mean in the real world, not in the math world we're dealing with here. So, second scenario. Marissa dumped some stuff into Matt's beaker like she might want to from time to time without him looking, just to kind of mess with him. It's hilarious. I like the idea. And so Matt had 0.2 molar acetic acid, and she dumped in 0.5 molar sodium acetate. Sodium acetate, because it's a group 1 salt, breaks apart very well. All of the sodium and the acetate separate, so there is already acetate here in the solution now. That means that it can't shift as far because there's already a little bit of product over there, right? Not all of us use product. Some people do use, but never mind. So this x value, 0.2 minus x, again, x is going to be ridiculously small, but on the other side, it even becomes easier, 0.5 plus x. What is 0.5 plus ridiculously small? Now, 0 plus x is still x because x is way bigger than 0, so we still keep that. Look how much easier the math just became. We don't even have to take a square root this time, Arthur. We can just cross multiply the 0.2 and divide the 0.5, and x is by itself. Does that make sense? And then what could I do with this value? If I take the negative log of that, I'm taking the negative log of hydronium, and I've got the pH. Look at the drastic difference in the pH. When Marissa added this acetate, when Matt wasn't looking, the pH went from 2.7 to 5.14. It really impeded the acid's ability to react. That's pretty cool, isn't it? It slows it down. And what we have created now in this second scenario, what Marissa created, I didn't create it, she created it by messing with Matt. She created what's called a buffered solution. A buffered solution has an acid and its conjugate already present. It has both present in the solution. The conjugate can take hydrogen, and the acid can give hydrogen, and you have both in there. And these are actually really easy to calculate the pHs. I'm going to show you a trick in a minute to how to calculate them. You know what? Let's actually go through this. Let me just clear all those things out. Oh, some of you maybe just paused. Others can't. So let's fill in the gaps here. Let me call on someone here. Yeah, Casey. There you are right there. So Casey, what is the HCOOH value from this question? 0.250 molar. All right. Do we have any COOH? -1 from the question. This is sodium and formate. That's what COOH is. And so there's 0.1 molar formate from the sodium formate there. And so we would lose some of this, we would gain some of this. There's no hydronium except for a tiny amount naturally occurring in water. So 0.5 minus x is 0.25, I mean 0.25 minus 0.100. What goes on the top here is the 0.100 times x, 0.200. I should pick up my calculator and do some math, which is good because you guys are writing stuff down and would prefer that I slowed down anyway. All right. Yes, Casey. Yeah, 0 plus x is still x because the amount of H3O in the water is so small. Yeah, it's practically 0. And the value we're adding to it, it turns out is 4.5 times 10 to the -4th. And that's way more than the amount water makes. The water makes 1 times 10 to the -7th when it's by itself. So that's 1,000 times more than that. So the amount contributed by water is negligible. So the pH was pretty good. You got me. The pH is 3.347. That seems like a lot of work just to find a pH, doesn't it? So there's an equation we're going to use. It's on the equation sheet. It's called the Henderson-Hasselbalch equation. And it simplifies our math, which we always love when an equation simplifies our math. What? You thought it was Hasselbalch? Hasselbalch? Hasselbalch. Hasselbalch. Yes, Arthur. This was actually a 5-0, so there's 3 sig figs, so I did 3 decimal places. It might be off by as much as 5%, but the only difference would be there at the tail end, right? And you want to know whether or not the pH is 1, 2, 3, or 4. You're not really too worried about the 4.7 on the end. You're worried about the 3.3 on the front end. So here is the Henderson-Hasselbalch equation. It's just a little bit lower in your notes. You can find it right here. It is on the equation sheet. And the Henderson-Hasselbalch, it's actually all one word. I think I got auto-corrected. Hasselbalch? The David Hasselhoff equation? Germans love the David Hasselhoff equation. You probably don't even get that joke, do you? Do you know who David Hasselhoff was? Oh, let me pause for a second. The Hasselhoff. So what we do is we will plug these numbers in. This value is the anion, COOH negative, A negative. This is the acid, H in the anion, H in the anion. They picked A on purpose. It stands for anion. Anion, negative anion, A negative ion. That's the anion. H in the anion, there's just the anion. Right? You got me? Good? This is 0.1. Plug in 0.1. This is 0.25. Plug in 0.25. This is pKa. This is the P of anything. You take the negative log of the thing to get the P of the thing. Right? What's a P Spencer? Negative log of Spencer. Right? What's P cabin? Negative log cabin. Yes. So here is the pKa, the negative log of Ka, the log of this times this. And what they're really doing, Dana loves logs. It was her favorite part of math. Right, Dana? Matt told me all about it. She said, oh, I love logs. And Matt was like, yes, she does. I don't get it. And so if Dana took the negative log of all of this stuff up here, she would be doing this. She'd be doing like, subtract over, and then she'd be doing all this. And so what Henderson, David Hasselhoff Beck did is they just kind of put it all together in one equation so you didn't have to do all the manipulation. Does that make sense? This equation is given. Only use this equation if you have an acid and its conjugate already present. Okay? A. All right, we're about to change gears drastically. So before I change gears, I'm going to set the scenario for the lab. Yes, Casey?
So you said that only the acid and conjugate base?
You have to have an acid and its conjugate base. There is the reverse of this equation. There is the base conjugate acid version of it. It's not given on the equation sheet. It pretty much looks like the same thing, though. It's... hope I get this right. It's POH equals PKB plus the log of HB over B, meaning like hydroxide and then the acid it makes, because you'd put the base in and then it would make a conjugate acid. So it's pretty much the same, but everything's been reversed. Yes, Tyler. That's funny because I accidentally call him Tyler on a regular basis. Yeah. Yeah, using the rice table and subtracting out the x values and stuff like that works fine too. Yeah. Goodbye. Oh, no. Yes, you may. That's all recorded now. So, in our lab, what we're going to do is I am going to give Andrea a beaker of acetic acid. She's going to stick a pH probe in there. Guess what she's going to find of the acetic acid or the pH probe? It's acidic. He did like the Squidward hands. That was Jordan Mazza with Squidward hands. And then if she knows the pH, she could figure out how far it shifted, couldn't she? She knows how much hydronium's in the water. She could actually do kind of all the shifting. So now she knows the molarity of the acid that's in there because she knows the pH of the acid, assuming she knows the volume. More on that later. That sounded like I just said moron. More on that later. However, she's not just going to do that. She's going to then slowly add sodium hydroxide. Adds 2 milliliters. The acid and the base have a fight. What do acids plus bases make? Water. They make water. They neutralize each other to make water. So if she starts off with 100 moles of acid and she adds 2 moles of base, they have to completely react. Which one are you going to run out of? 100 moles or 2 moles? And so you end up with 0 moles of base and 98 moles of acid. True? And it's a weak acid, so the pH is still kind of weak. And then she adds more base. Acid still wins. And you keep doing this over and over again. Add a little bit, write down the pH, write down the volume. Add a little bit, write down the pH, write down the volume. Add a little bit. You're going to do this, I don't know, 40, 50, 60 times. Yeah. You're going to do little additions, pH changes, write it down. And Mr. Murphy, the pH is changing constantly. It's like 2.71, 2.72, 2.73, 2.71. Make a decision. That fluctuation is natural because we have a plus or minus of 5%. Should I have my stirring bar on high? Probably not. You will have a magnetic stirring bar in there spinning around, but you don't want to have it going like, I wonder what that sounds like later. You want it on low, just agitating the solution. If you actually spin it on high, it'll pull air into the water. Carbon dioxide reacts with water to make carbonic acid. You'll actually be acidifying your water. So you want it on slow, so you're just gently mixing the acids and bases. Yes, Arthur. Side note? Wait, should I record this side note? Okay. And that's when we found out Neil was in ruckus. So with acid-base reactions, when you actually have an acid added to a base, you have to figure out which one you're running out of. And the only way to do this is in terms of moles. Because you have a beaker with a solution in it, some volume, and you're adding a different volume of base. Volumes have molarities that are different. You actually have to calculate how many moles are in each one. So we have a new type of table to make called a BCA table, before, change, after. It's similar to a rice table, but it's mole based. So in this scenario, Lila has 1 liter of 5 molar acid, HA, and 1 liter of 1 molar base, BOH. She's mixing these together. So we need to figure out how many moles are actually being mixed. So we use the molarity times volume equals moles equation. So we're going to ask Evie, who's just walked in, what is 1 times 5? 1 liter times 5 molar is 5 moles of acid. 1 liter times 1 molar is 1 mole of base. So am I going to run out of acid, or am I going to run out of base? So you always figure out which one's limiting it, and that's what you subtract from both. Because you have like 5 moles approaching 1 mole, they fight, the base knocks out all of the acid it can. Or reverse. So the base can neutralize 1 mole of acid. How much base is left over after the reaction is complete? 0. How much acid's left over? 4. However, we have a reaction now making product. So we just made 1 mole of anion, didn't we? What we have left over is a weak acid and its conjugate base. This feels like a scenario we just had involving days of it halves off. We've just reached a point where we have acid and its conjugate, so we can use the Henderson-Hasselbalch, whatever, equation again, but this equation in terms of molarity, so we should probably divide these moles by the volume. Dana, what is 1 divided by 2 divided by 4 divided by 2? Simplify into 1 divided by 2 divided by 4 divided by 2. What could you eliminate? The 2's. So really it's equal to 1/4, isn't it? Since these volumes are mixed, dividing by the volume ends up canceling out inside this equation. So you could actually just do 1 divided by 4 in the equation, and then you could do this part right here, because you're mixing everything into the same flask. Up here it does make a difference. You have to know the specific amount of moles that are being mixed together. So in our lab, The first step is figure out the pH, and from the pH she can backtrack and calculate the molarity. If I give her 100 milliliters and she knows the molarity is 0.1, she can do 100 times 0.1 to figure out the moles. And then she adds 2 moles of sodium hydroxide, knows how many moles that is, 100 moles minus, let's say, 2 moles, now 98 left over, and she could play that game the whole time. She's going to collect data, a whole range of pHs that hopefully match with the math she can also do to test it. All right, so hopefully the data we collect matches the math we can do. Does that sound fun? If you think that sounds fun, you have problems. It just sounds like a lot of math. But this is essentially the lab, like math post-lab. And you're not going to do, how many data points did I say you're going to collect in the lab? Like between 40 and 60? You're not going to do 40 or 60 calculations. You're going to pick a couple of spots along the way. And you go, okay, at 15 milliliters, how many moles of hydroxide had I added? Subtract. How many moles did I make? Calculate the pH. Does it match? Yay! Or no. And then one of the primary reasons it might not match is what if your pH probe is not calibrated correctly? Maybe a problem. All right. So here we have one that's all worked out. I'm just going to leave it up here for a second. Let you guys copy some stuff down. I'm just going to pause video-wise so you don't just hear silence. That was a funny story, Wahaj. Thanks for telling us that. Casey's not going to be happy you shared that one. What we have going on in this scenario is it's kind of like our lab where we have a beaker, and in this beaker is a solution. So this is in this beaker. The volume of this beaker is 500 milliliters, and it has 0.2 molar formate and 0.1 molar sodium formate. We have to convert and figure out how many moles are present. So moles are equal to, N is equal to molarity times volume. That's what's going on here. Molarity times volume, molarity times volume. Why are these both 500? They're in that beaker. Okay, they're in this beaker together. They're in a 500 milliliter beaker. We've been told their molarities. And then slowly, we'll go to Katrina. I haven't used Katrina's name in a while. She's also absent today. Katrina is adding 6 molar sodium hydroxide. And so 6 molar times 10 milliliters of sodium hydroxide she added is 0.06 moles. So we write down all those moles in our BCA table, before, change, after. And this is what we have before, this is what we have before, and that was already in there. Which reactant are we going to use up or limits the reaction? The 0.06. The hydroxide. The hydroxide and the acid are going to react until one of them is used up in just ridiculously small. So 0.06 gets subtracted from both of them. It's always going to be a 1-to-1 ratio with acids and bases, because one acid can only react with one hydrogen, can only react with one hydroxide to make water. So I subtract 0.06 from both of them. I'm making 0.06 on the other side though, because I'm making products from these reactants. And what I have left over, just like the previous example, is a weak acid and its conjugate base, which then means I'm allowed to use the Henderson-Hasselbalch equation to do the math. Yes, the volume totals up. We have 500 milliliters plus 10 milliliters, so the volume is now 510 milliliters. But you end up dividing the 510s into each other in this equation when you convert them to molarities, and it's like they cancel out. And so we can calculate the predicted pH. That is slightly higher than it was before. I need a calculator. Before the base was added, let me just do some math real quickly. Before the base was added, negative log of 1.8 e to the negative fourth plus log of so before this tiny amount of hydroxide was added, before this, when it was just HA and A, the pH was 3.35. 3.4. This is what we saw in the previous example. Meaning in the previous example that we worked all the way through, we worked out the pH if it was pure. This is like step 1 of our lab, where what's it if it's pure? And then, now that some hydroxide's been added, look, the pH increased, didn't it? Did it increase drastically? It went from 3.347 to 3.97. It's not going to increase drastically because we have a weak acid and they help resist pH changes. That's what we call a buffer solution. Where do you guys have buffers? You guys know of any buffers? You guys use buffers constantly inside your stomach lining. Your stomach is filled with what? Food and hydrochloric acid, hopefully some food. And the hydrochloric acid is being contained by the stomach lining. The stomach lining is a series of buffers, and there's basically a sacrificial layer of cells filled with a buffer solution that kind of fight off the acid. And then when they lose, they get absorbed into the acid, and a new layer advances, just like your skin, but in the stomach. And there's a constant replenishing of that buffer solution. If your stomach can't replenish it, you then get an ulcer, and then the acid has eaten its way through your stomach and is now leaking into the rest of your body. Ow, that hurts. So then they have to do surgery on you and sew the hole shut. All right, that's not good. We're actually going to skip this because it is wrong. Here we have another example, but I think I typed this incorrectly right here. Give me a second. Let me pause for a second. So there's 2 parts here. Part 1 is we have sodium cyanide and then we have hydrocyanic acid mixed together in water. We're given the Ka. Could we figure out the Kb for cyanide if we know the Ka for the hydrocyanic acid? Yes, we could. I'm going to do some math. I'm going to change those masses into moles and divide by the volume to get molarities. I'm going to pause because you don't want to watch me do all that. So I converted those masses into moles and then divided by the volume, and then I could plug these 2 values and the Ka in and calculate the pH of the solution. Typing things in my calculator incorrectly will not help. Time I record, I find that the second I record, the classroom becomes intensely quiet. The pH of this solution is 9.113, which for a second I was confused, and then I looked at that Ka. Look at that Ka. It's pretty small, isn't it? Now, in the next thing, the second scenario, I have an acid being added, don't I? What do acids react with? Bases. Which is why I had to rewrite this question, because I had it typed up wrong. I did a copy and paste function in Word, and I didn't read carefully. So the A is the base from the previous question. And there were 0.825 moles of the base, and there were 1.375 moles of that acid, the weak acid. I need to figure out how many moles of hydrochloric are being added. So let's see, 50 times 3 divided by 1,000, convert it to actual moles. 0.15. 0.15 moles of acid, 0.825 moles of base. Which one should I subtract? Yep. Good job, Casey. I'm subtracting 0.15 from both of them. And then on the other side? Adding the 0.15, right. And so 0.825 minus 0.15, I should probably, oh, that's not the right thing. I converted this mass into moles to get the moles of acid and the moles of base. Right? So that's how many moles of base, conjugate base, and acid were in the solution originally before they added this hydrochloric acid. For this, yes, I did volume times molarity to give me the moles of hydrogen for the 0.15. Oh, that's the mistake. That there. Oh, darn it. Just kidding. So I accidentally wrote down the molarities instead of moles. This is supposed to be the acids moles. The acids moles. This is the anions moles. And then this is the volume times molarity. So I subtract 0.15 from both of them and then add 0.15 to this side. 0.644 minus 0.15. 0.825 plus 0.15. So now I can take these values and plug them into the Henderson-Hasselbeck equation just like we did a second ago and calculate the pH. I'm taking the log, and this needs to be the anion over the acid. So 0.49 divided by 0.975. Should the pH be going up or down? Before I write the answer, I know none of you have your calculators doing this. Should the pH was previously 9.113, what are we adding? Acid. So we're expecting this to become more acidic or less? More, and it does. It's become 8.909. That's not a huge change, is it? No, because bases, the weak acids and bases really resist pH changes until you use them up. What do I mean by use it up? How many moles of acid or base? You've got to use them all the way up before you see a huge pH change. So if they had added 0.644 moles of hydrochloric acid, then there would be a 0 here and a 0 there, wouldn't there? What if they add 0.65 moles of hydrochloric acid? You would use all of this up, and you'd have hydrochloric acid left over, and the problem actually becomes a lot easier. Yeah. 0.15 is volume times molarity. It's got to be in moles, not millimoles. So I made sure to divide by 1,000. That's one thing I did correct a minute ago. Good catch. Was it Patrick that caught that? That was Colin. Oh my gosh, Colin, I haven't seen you there the whole time. Good hair. Like it. Sweet playlist. All right, let's shift to the next question, which actually has something interesting occur. The Ka of, I don't know what the name of this acid is. That drives me nuts. C3H5O2. That's not acetic. I don't know what it is. I should probably know that. No, it's not pyruvic acid. No. What is the pH when this value equals this value? If the acid is equal to the anion, what would happen if they were equal to each other? They would cancel each other out. And you'd have the log of 1. The log of 1 is 0. And therefore the pH would be equal to the pKa at that point. This has got a specific name. It's called the midpoint of the buffer. That's where you've used half of your acid up and made an equal quantity of conjugate. And that's kind of like the sweet spot where the pH really is resisting change the most. When we do our lab, this is volume, and this is pH. And we are going to do the lab with acetic acid and sodium hydroxide. And so you'll start off with a pH maybe about 2, and you'll slowly be adding sodium hydroxide to it, and you'll see this happen. You're not going to get a line, you're going to get a series of dots as you like record the volume you added, record the pH. Record the volume, record the pH. So, and let me just throw some random values on there. Here we have like the sharpest climb, right? And that appears to coincide to a pH of like 9 or 10 or something like that. And that's what we call the equivalence point. Maybe that volume is, pick a number for me, Minu. 20, okay? So 20 milliliters, and then halfway is this, where you've used half of your acid up, or half of your base up, whatever the weak thing is you have in there. In this case, we had a weak acid, because you could see it starts on the acidic range. This is a very common graph. You see this slow increase, it flattens out almost, and then a slow, whoa, drastic increase. At the equivalence point, the acid that you started with is equal to the base you have added. All right? And if they're equal, the acid and the base have neutralized each other, but there's plenty of anion left over. And what did we say these anions can do to water when they're by themselves? They could take some of the hydrogen from the water and they leave behind hydroxides, which is why the pH isn't 0 when they're isn't 7 when they're equal. It's actually above 7, because when they're equal, now the thing that's left over is the anion that's going to gobble up a couple of hydrogens and raise the pH to like 9 or 10, which is not that extreme. A very common graph, and we're actually going to skip this. What's that, sir? So this is actually the same graph a couple slides forward. This is a weak acid. You see this like kind of curve, and then extreme climb with a strong base. So you have a kind of a curve at the beginning and then a giant jump to the basic side. So that's a weak acid versus strong base graph. Very characteristic. You'll see that depending on, no matter what the weak acid is, you kind of have this curvy part in the beginning and then the giant jump. If it was a weak base, you'd see the reverse. If it was a weak base, you'd see a tiny dip, a flatten, then the giant jump as it becomes acidic and the acid wins the fight. So this would be weak base versus strong acid added. They're adding the strong acid. You almost always titrate by adding the stronger thing. The titrant, the thing you're adding, is usually the stronger thing. We use indicators. Indicators help us see when the pH is changing. We will probably use phenolphthalein. Phenolphthalein changes from clear to pink at about 8.5. So we'll know we've just blasted through neutral. The burette will contain the strong base. The flask will have the weak acid in it. That's a titration curve. When we graph this data, we will not be adding a line. We'll just be adding the dots, because there is no mathematical equation for this, because it's actually two different completely math problems. You've got the weak acid, then it eventually loses and the strong base takes over. So it's actually two different math problems. So you can't graph it with a line. You can just graph the dots and then you come back with your pencil or pen and draw the line. Some people don't like that. This is a characteristic graph for strong acid, strong base. Strong acid, strong base. What's different about the beginning? Do you see the curvaceousness in the beginning? You don't see this in the beginning? It's flat almost, isn't it? And then the base wins and it shoots up. And the difference with a strong acid is its conjugate is weak, and a strong base, its conjugate is weak. So neutral ends up being a pH of 7. Equivalence point ends up being a pH of 7. All right. Did everybody grab the homework?